All right, we're going to start off here today with some modeling with exponential and logarithmic functions. Mostly going to be exponential here, although we'll be using logarithms to solve them. So our main formula here is for radioactive decay. So you have it right there. We have m of t, and so this is going to be the mass at time t. And then the m sub 0, this is all kind of one variable there. M sub 0 is the initial mass. E, of course, is not a variable. It's our exponential constant number. And then to the power of negative RT, t is going to be time here. I'll write that over here. T equals time. And I'm going to write there, just make sure with the time you're consistent. We saw in our earlier formulas, this unit for compound interest, that time has to be in years. In this one, it actually does not have to be in years. It just has to be consistent throughout the problem. So we'll be seeing some examples of that as we go along here. R is the decay rate, but it's going to be defined by ln of 2 divided by h, where h is the half-life. So half-life is the amount of time that it takes for the radioactive material to be cut in half. So that is that. Okay, awesome. So we'll take a look at some problems here then, just using this formula. So it says here polonium-210 has a half-life of 140 days. So that's a key figure there. That's going to be our H. Suppose the sample has an initial mass of 300 milligrams. So that is our M sub 0. Okay. So let's go ahead and build our function here. Now notice that we didn't use this 210 here. The 210 is actually the name of this. I'm not a chemistry expert, but I think it's the name of this particular isotope, and it's the atomic mass of it. So it's actually not relevant to the problem here. So we can go ahead and build our formula here. So I'm going to say m of t, and this first question is just asking for the formula, equals our initial mass we know is 300, so it's going to take over for the m sub 0. Remember, E is going to stay there. It's not a variable, it's a constant. And then the negative, and I'm going to just put here ln 2 divided by the half-life, which is 140, times t. And I'll put that up there in the exponent. I'm going to go ahead and use parentheses there. I know that when I do this in my calculator, it wants the parentheses there, so I'm going to put it in my formula. So that is the formula there. I could plug in any t I want, and it will tell me the mass after that time, as long as t is in days. So I'm just going to make a note for myself there that I always need to consider that. Okay. So then part B here says find the mass after 1 year. Now that's where this comes into play. This is actually going to be m of 365 because our half-life is in days, so we've got to convert the year into days, and that's what that's telling us, is that t is 365 days. So we got to be consistent there. Since our half-life was in days, we got to plug in times that are days. Okay, so we'll do 300e to the power of negative ln 2 over 140 times 365. From there, I'm just going to type this into the calculator and see what it does. If you're going to use Desmos, you can actually just type the button E for your what is it? For E. If you are using your calculator, it's second ln will give you the E button there. Okay. All right, so when I get this out here, I get 400, or not 400, but just 49.24, let's call it, if we round it to 2 decimal places, and that's in milligrams is the mass here, just kind of the same as it was in the original. Okay, next up, how long will it take to decay to 200 milligrams? So we're going to plug in 200 up here for the mass, and we're going to solve for t. Okay, so we get negative ln 2 over 140, and now t is back to just being t. Okay, and so I see here my variable is in the exponent, so I know I'm going to need to use logarithms to solve this. I know that my The base of my exponent is e, so I'm going to use a natural logarithm. But first, I need to get rid of the 300, so I'm going to divide the 300 over to the other side. And I'm just going to call that 2/3. So 2/3 equals e to the power of all of that. Now that I've isolated the base, we're ready to switch it into logarithmic form. So it's going to be log base e, so I'm going to write that as ln. And then the new partner is going to be 2/3. Remember that this ln is an implied base e. And then what was in the exponent is now isolated over here all by itself. And there we go. Okay? All right, so then last step here is that I need to isolate t. So I'm going to multiply by the reciprocal here. So I'm going to multiply by 140 over negative ln2. And I'll, of course, multiply that over here as well. Multiply by 140 and then divide by negative ln2. These will cancel out over here, so this is pretty much going to be what my t value is. I can just type that all into the calculator. 140 times ln of 2/3 divided by negative ln of 2. I know it doesn't make sense for time to be negative, and we have that negative down there on the bottom, but I know that ln of 2/3 is actually negative, so it'll be a negative divided by negative and kind of work itself out, which usually in these cases it will, so don't panic if you see a negative kind of in one spot, because it might cancel out with another negative somewhere else. So this is going to be 81.89 days. And so there you go. I say that the part of a day is kind of is logical because you can break down the days into hours or minutes or whatever. All right, next up here, it looks like we have 100-gram specimens. That's our initial mass is 100. We have the half-life of 2.6 years. So we'll build another formula here. This is Na22, so that's just, once again, the 22 is the name of this particular isotope. I think Na is sodium. And so we'll go m of t equals our initial mass, and then times e to the power of negative ln2 over 2.6 times t. So once again, going with our formula there, we know that r is defined by negative ln2 divided by whatever the half-life is. All right, after a decade, we know that a decade is meaning that it's 10 years. So I'm just going to do m of 10. Okay, 2.6 and then times 10. And we'll just type that into the calculator and see what we get. So when I typed that in the calculator, I got 6.95, and that is going to be in grams, because as you can see there, the initial mass was in grams as well. All right, so how long will it take until it goes to 5 grams? So once again here, we're going to go back to our formula from part A. I'm going to plug in 5 for the mass. And it's going to solve a lot like the previous question on part C. So if you want to pause it here and try it on your own, you certainly can. I'm going to go ahead and just divide the coefficient here. We'll get rid of that. You can do a decimal for that. You can just leave it as 5 over 100. You can make it 1 over 20, whatever you want. I'll just go ahead and leave it as 5 over 100. Okay. All right, so now we've isolated the base. We're ready to switch it into logarithmic form. So it's a base e, so it's going to be a natural log. And then the other side of the equation is going to be inside of there. And then what was in the exponent is now isolated, which is kind of the whole point of logarithms. Okay, and then last step here, we'll go ahead and just multiply by 2.6 over negative ln2 on both sides. You can cancel those out, and there's our answer in kind of the long form, and then we'll go ahead and type it in to the calculator to get a decimal for that. So we got 2.6 and 5 over 100 inside of the natural log divided by negative ln2. So I got for that one that it is going to be t equals 11.24 years. I know it's in years just because that was what our half-life was in. Okay, so a very important application of radioactive decay and understanding these models is carbon dating. So I got a nice little cartoon here. Carbon dating is when one carbon asks another carbon out on a date and maybe they go see a movie, go out to dinner or something. No, just kidding. Carbon dating is actually when an animal or plant dies, it stops exchanging carbon with its environment, and the amount of carbon-14 it contains begins to reduce and undergo radioactive decay, just like we talked about on the last page. Measuring the amount of carbon-14 in a sample from a dead plant or animal, such as a piece of old wood or a fragment of bone, provides information that can help calculate when the animal or plant died. So the key there, we know that for all of these, whenever we're talking about carbon-14, the half-life is approximately 5,730 years. So that is going to be our H. So for each one of these, we know that our R is going to be negative ln2 divided by 5730. Okay, so let's go here. So for this one then, we know that our equation is going to set up as, and I'm going to go ahead and leave, we'll go m of t here. Actually, we're not going to go m of t there. Yeah, we will. Go ahead and put that. And then here I'll put m sub 0, which we'll talk about in a second. And we know this is going to be negative ln 2 over 5730 times t. Now, let's talk about the m sub 0, the initial mass, and then the mass at the end. Now, this one does not give us actual masses. It just says that 25% of the original carbon-14 was present. And so, from some unknown amount that we don't know to start with, we have 25% of it kind of left, okay? So, a couple things we could do here. The way you might think of it is, well, let's say we started off with 100, and now we have 25. I think that would work, and that's a logical way to do this. And so that's just saying that we have 25% of the original carbon. So if we start off with 100, now we have 25. What I actually think is an easier way to do this, or you could actually do it where the m sub 0 is 4 and the m of t is 1. You can see that is kind of 25% of it as well. But what I think is the easiest way to do it on something like this is just make your initial mass 1, and then I'm going to make my m of t be 0.25. And so that's the one I'm going to be using. Any one of these would work, but I think you're going to see here when I put this at 0.25 and I put this at 1, it's the easiest way to do it, and the reason why is this 1 is actually now irrelevant. I can actually scribble it out. And if you think about if I would have put 25, or I would have put 100 here and 25 there, when I divided that over, it would have been 0.25 at the next step anyway. Same with the 4 and the 1. If I would have put 1 here and 4 there, I divide the 4 over and it would be 0.25. This way I can just save that step and scribble out the 1, since multiplying by 1 is really irrelevant here. That's the only number when it's multiplying that I would be able to scribble out. So that's why I use that, and then just put the decimal over there of the percentage, okay? All right, so now then we're just ready to switch it into logarithmic form. So I'm going to say ln of, so the base is e here. But it's going to be 0.25 inside of there, and we got what was in the exponent is now over here. So solving now a lot, or not a lot, but exactly like we did on the previous page. So now I'm just going to multiply both sides by 5730 divided by negative ln2, and that will cancel this out. And so I get t equals all of that, which I can type in the calculator now. And this should give me my answer here. Negative ln2. Okay, so I get 11,460 years old. Awesome. So you'll kind of hear a lot about this on the news, that they determine the dates, and they say, okay, this artifact is 11,000 years old or something like that. And this is how they know that, is by the carbon dating. All right, so very similar on this one here. This one just says they have 28% of it left, so I'm just going to put 0.28 out here. And then it's going to solve kind of the exact same way. Once again, when I have a 1 here, I can scribble that out. I wouldn't be able to do that with any other number, but with 1 you can, just because in terms of multiplication and division, it's irrelevant. So then I could say ln of 0.28 equals negative ln2 divided by 5730 times t. And we'll multiply by the reciprocal there, 5730 over negative ln2, both sides, of course. I'll cancel out, and I'll get my t value here. So really just the same thing I did last time, except 0.28 now instead of 0.25. So we get 10523, and then 0.15 years. So nice and simple there as well. Okay, next one here. This one's a little bit different, so pay attention to this one. And so this one is saying that 90% of the original carbon-14 has decayed, and so that means that 90% is gone. But what that actually means is that, and what's more important for us, is 10% is left. And so for this one, I'm actually going to put a 0.1 up here and then a 1 right there. So it is the same as the previous ones. It's just you got to watch out for that wording there. If they say that this is the percentage that is gone, has decayed, you have to put the percentage that's left. You can see on the other ones, they say that 28% of the original carbon-14 was still present. So that's like 28% was still there. This one's saying 90% is gone. So be careful about that wording there. Okay, so then I'm going to do ln of 0.1 equals negative ln2 over 5730 times t. Once again, multiply by the reciprocal there. All right, and we'll type that into the calculator here. So that's 0.1. And that one is going to be 19,034.65 years old. All right. All right, the last thing we're going to be going over here is called Newton's law of cooling. It's also based on an exponential function we're going to see on the next page with E. And it's so let's take a look at that. All right, so here's the formula for Newton's law of cooling. We have it right here. So we got a lot of variables here, a lot of the big T's, and so we need each one is different. So T of T out front is the temperature at time T. So that's where we're gonna be kind of plugging in our or getting out our temperatures at the end. Okay, T sub S, which does show up there twice, is the temperature of the surroundings. So if you're putting it in a room, it's the temperature of the room. If you're putting it in the oven, it's the temperature of the oven, because now it's surrounded by the oven. T sub 0 is the initial temperature of the object. Anytime you see that sub 0, that's almost always the initial. And then K is the cooling rate. You could call that R if you wanted to. I think I've seen sometimes where they use R, whatever. It doesn't really stand for anything with the K. R might be better since it's the rate. And this is different for every object. And that's actually not surprising if you really think about it. Because I always think about kind of in my house, I have carpet in the bedroom. And so whenever I get out of bed, I put my feet on the ground, it feels not too bad, even if it's a cold morning. My carpet feels fine, but then my hallway is made of tile. So when I step on the tile with my bare feet, then it's super cold, and I'm like, oh no. So that's just because the tile is cooling down at a quicker rate than the carpet. Okay, a key fact here, which I would definitely highlight, I like this one, is that the parentheses there, this is going to be positive if the object is cooling down. I probably should have done that let's do that in blue actually. So it's cooling down, then that parentheses should be positive in there. And if it's heating up, it's going to be negative. Okay. So although it's called Newton's law of cooling, it works the same way if the object is heating up instead. All right, so we got our first problem here. So we got a cup of coffee, it has a temperature of 200 degrees Fahrenheit, placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the coffee is 150 degrees. So for this one, what I notice here is a couple of things. The first thing I notice is that we have our T or 200 degrees is going to be our initial temperature. That's our cup of coffee. So T sub 0 is 200. It's placed in the room that's 70 degrees, so the temperature of the surroundings is 70 degrees. It does not tell us K, so that's going to be like our first goal here in this case is to find K. But it does tell us that after 10 minutes, so it's going to say T of 10, so after 10 minutes, it is, what, 150 degrees, okay? So I'm going to kind of take the formula and plug in everything I know here. So we have T of T equals, and I'm going to, let's see, we got T sub S first is 70 plus, and we have T sub 0, so 200, minus, and then 70 again, e to the negative kt here, okay? And then I'm going to plug in my point, okay? So they say that when I plug in a 10 for time, I get out a 150 for temperature. So I'm going to plug in 150 over here. I'll go ahead and simplify this. I'm going to call this 130 times e to the negative 10t. So the 130 I got from inside the parentheses here is 200 minus 70, so that's 130. So as we said, this parentheses will be positive if the object is cooling down, which is what's happening here. We're getting the hot coffee and putting it in the kind of regular temperature room, so the coffee is going to cool down. So now, oops, and you know what else I messed up here is this one is actually supposed to be K. I filled out the negative, or sorry, I filled out the 10 for T, and I moved it out front, but really what's left there is K. So now I need to solve for K. I'm not allowed to add these two together because the 130 is attached to this. I'm always going to subtract this number over and then divide that one. So I'm going to do that right now. So minus 70. That's going to give me 80 equals 130 e to the negative 10k. And I'm going to divide by 130. I'll go ahead and reduce that to just 8 over 13. Now I've isolated the e here, so now I can switch it to log form. So I'm going to have ln of 8 over 13, and what was in the exponent is now isolated. And lastly, I'm just going to divide by negative 10, and that's going to be my k value. So part A here asks me to write a function, and so I'm ready to do that now that I have my k value. So I'm going to say t of t equals 70 plus 130 e to the power of and then I notice up here that it's negative k times t, so I'm actually going to go back here and if I look back here, I had k equals that, and so I'm going to say negative k equals ln of 8 over 13 divided by a positive 10. So if I would have then multiplied both sides by negative 1, I think that makes this a little easier to visualize. So then I know that what I'm actually putting up here is negative k. So negative k is ln of 8 over 13 over 10, and then times t. So that's going to be my formula there. If I was kind of to strictly go with this, it would have a negative in front here and then a negative down in the 10. So it kind of like those cancel out. Negative divided by a negative is a positive, so I'm just going to put it as a positive. Okay, next up here, part B says, what's the temperature of the coffee after another 15 minutes? And so that's kind of important there, another 15 minutes, because I already had 10 minutes pass by. And so this is actually T of 25. Because it's saying, you know, the 10 minutes at which it dropped down to 150 plus another 15 minutes, what's the temperature going to be? So there we go on that. E to the ln of 8 over 13 divided by 10, and then times 25. So I'll just go ahead and type that in my calculator now and get my answer. All right, so I got that it is now 108.62, and that'll be in degrees Fahrenheit. All right, next up here, part C, saying when will the coffee be at 100 degrees Fahrenheit? So for that one, I'm going to go back to my original formula here on part A. And I'm going to plug in 100 in for the temperature, and I'm going to solve for T. All right, so like we did when we were solving for K, we're not allowed to add the 70 and the 130 together. So instead what we're going to do is we're going to subtract the 70 over here. So 30 equals... and I'm going to divide by 130. I'll cancel those out, the zeros there. So now I've isolated the base here, and so I'm ready to switch it into log form. We have a log of base e, so I can switch it into an ln, and then the 3 over 13 is going to go inside of the ln, and then that's going to be equal to whatever was in the exponent. So what was in the exponent was ln of, and let me get some more space here, 8 over 13 divided by 10 times t. So now it's still a fraction, but it's out of the exponent. So now to isolate t, I'm going to multiply both sides by 10 over ln of 8 over 13. We're going to multiply by the reciprocal there. So I'll just type that into the calculator. 10 divided by ln of 8 over 13 times ln of 3 over 13, and that'll give me my t value. So I'm going to type in all of this right here. Once again, 10 divided by ln of 8 over 13 times ln of 3 over 13. All right, so when I do that, I get that t equals 30.2 minutes. So from when I initially took it out of the coffee maker. All right, similar question right here. So we got a can of soda. It's taken from a 35-degree cooler and put it at the pool party, which is 90 degrees. So actually this one's a little different because it's heating up. So this is our initial temperature there is 35. And then the temperature of the surroundings is going to be 90 because that's where we're putting it at the pool party. And then they tell us that T of 14 equals 53.5. Okay, so very similar to last time. I'm going to just plug in what I know here. So I'll just start off by saying T of T equals, and then according to the notes, it's the temperature of the surroundings. So that's going to be 90 plus, and then in parentheses here, and we have the temperature of the object minus the temperature of the surroundings times e to the power of negative kt. All right, so now I'll plug in my point and I'll simplify the parentheses. So my point here will be 53.5 equals 90 plus. And actually, it's not going to be 90 plus. It's going to be 90 minus. So I'm going to go ahead and show that. And 35 minus 90, I don't want to mess that up. So I'm going to use my calculator for that. Negative 55, yeah, that's right. So 90 minus 55 times e to the negative kt. Now, oops, and that's not t. I'm going to go ahead and plug in here a 14. Okay, so now we're going to isolate k here to figure out what that is. So I'm going to subtract 90 from both sides. Minus 90. Okay. So negative 36.5 equals negative 55 times e to the negative 14k. And then we will divide both sides by negative 55. I'm just going to leave that as a fraction on the left-hand side. And now I'm ready to switch it into log form since I've isolated the e. So it's going to be ln of, and I'm just going to write that then as positive 36.5 over 55 since it's a negative divided by negative equals negative 14k. And I'll just divide by negative 14 on both sides. And actually, you know what I'm going to do here? I'm going to just divide by a positive 14. And so that's going to give me here a negative k equals all of that stuff up there. So the negative k, like we saw in the last problem, is a little bit more valuable here because that's what I'm actually going to plug in the formula. So now we're going to say for our formula here that we'll use for the rest of the problem is T of t equals 90 plus, and I'm going to switch that again, so it'll be 90 minus 55 times e to the ln of 36.5 over 55, and then that's going to be divided by 14 and then times t. So then remember again, even though that's a negative k in the formula, I did solve back here for a negative k, so that's why I'm putting it in there as that. Okay, so now it's asking me when will it reach 60 degrees, so I'm going to plug in a 60 for t. So we get 90 minus 55, e to the ln of 36.5 over 55 t over 14. Okay, so now we will subtract the 90. So negative 30 equals negative 55, e to the ln of 36.5 over 55 over 14t. Okay, now we divide by negative 55. I can go minus minus to plus plus there. These cancel out. Now isolated the e, so I can switch it into log form. So it's going to be another ln. So ln of 30 over 55 equals, and whatever was in the exponent. So ln of 36.5 over 55 divided by 14 times t. So now to isolate the t, I'm going to multiply by the reciprocal of that fraction that's attached to it. So we're going to multiply by 14 over ln of 36.5 over 55. And so that's going to give me my answer here. 14 divided by ln 36.5 over 55 times ln of 30 over 55. All right, so I get t here equals 20.69 minutes. This answer is logical to me because it says that we're starting at 35 degrees, and then after 14 minutes, we're at 53.5. So then after 20 minutes from when we initially take it out, so it's about 6 minutes after this, we're up to 60 degrees. So yeah, that makes sense. So you got to drink the soda fast. All right.